really quick notes today. We're going to finish off with continuity. And so when we talk about continuity, the definition of continuity involves the concept of limits, which is why it's important that we do the limits prior to our discussing continuity. But the concept of continuity, once you get the hang of it, it's kind of a simple concept. So to define continuity, we have to have three things that are true. Three truths. All three of them have to be truths. I have to say yes to all three of these things in order for function to be considered continuous. And so the first thing is that I have to have in any given function a value at any a. So I say f of a exists. And to define that, what does that mean? That there is a value everywhere, or a value for every x. Okay, so it's not undefined, there are no holes, there's a value everywhere. The next thing is that there is a limit as x approaches a for that function. That means that there is a limit for every value of x. And then the last thing is that all over the value has to be the same as the limit. So that's defined as the value always equals the limit for every x. Okay, so those three things have to be true. I have to have a value everywhere, I have to have a limit everywhere, and the value always has to equal the limit. If a function is not continuous, we have different types of discontinuities. We have infinite, or where there's an asymptote. And so that would look like, here I have an asymptote, and here's my function, just sketching any one. But this is a function that is not continuous. Now there is a little bit of an asterisk that we can put here because they can define a function with an asymptote as continuous over its domain, because if a value doesn't exist in the domain or exist in the domain, then it's not part of its discontinuity. So there's just a little asterisk there that when you get into calculus, in calculus, not something that you need to necessarily remember right now, in calculus, they will sometimes refer to a function with an asymptote as continuous over its domain. Okay, this is kind of a side note, and it's again not something that we need to worry or concern ourselves with at this point too much, because we're just looking for the general definition of continuous. Is there a value everywhere? And this would fail because there is no value at that location. It also happens to fail because there's no limit at that location. So at this particular value of x I'd call a, there is no value and no limit. Okay, again, in calculus they kind of make some side notes to that. So a jump discontinuity, I always call that a break in the graph. And don't confuse a break with a hole. We're going to get to a hole as well. But a break in the graph is actually when the graph physically, you would have to like jump. If you could walk on this function, you actually have to jump to a different level to get, so there's a break in the graph. There's an actual visible separation between two pieces of a function. That's called a jump discontinuity. And then the last one is a hole, and a hole would be one where I have a hole in the graph. But notice the difference between these two, where, yeah, sometimes people consider, yes, this is a hole, I drew a hole, it's just that at this end point it doesn't exist, but the value exists down here. So in this particular function, there is a value for everywhere, or for every a. So there exists a value here. Even though there's this open circle here, it can't be closed because otherwise it would fail the definition of a function, but that's not a hole necessarily because I've got that value here. So this is a break in the graph where this is a hole in the graph. And it's referred to as removable because sometimes they can add a point down here at A where, yeah, I have a value, but in this location the limit at A goes to this hole, but the value is down here. I can still call this a hole or removable because on each side of that opening, that hole, this function goes to the same place. So notice again the difference between these two, okay? So now all we're going to do for this last section, and honestly this is going to go fairly quick, I spent more time explaining than what we're going to be doing. What they want us to do is look at this and determine if it's continuous, and if not, why not? And this is not continuous because we have a break, so it's a jump discontinuity. Done. There's a break in this graph. Yes, this looks like it's a hole, but remember this is a value down here, not the same as a removable. This is a jump discontinuity. This function here, I don't see any breaks, I don't see any holes, so we call this continuous. That's pretty much all we're working on. Go to another function. I look at the graph on this next page. Is it continuous? No. There's an asymptote. They call that, okay, so I say it was referred to as an infinite discontinuity. So an infinite discontinuity. On this one, no breaks, no holes. I've got this little bend in here, but that's not what this is all about. This one is continuous. Continuous. No breaks, no holes. What do I have here? A hole, so it's a removable discontinuity. So not continuous, it's a removable discontinuity. And this guy here happens to have two of them. It's got removable and infinite. So it's got removable at x equals 4 and infinite discontinuity at x equals 1. So this is not continuous. All right. Sometimes they'll be more specific, and the last few problems are more specific. They'll say, okay, at the given x values, so they're giving us the x values where I pointed out the x values on this problem. They're actually giving us the x values, and so at x equals -4, I have an infinite discontinuity. At x equals -4, and then at 1, oops, sorry, can't see that, and right here at 1 I have a removable at x equals 1. What do I have here? At 3, right here, do I have a break? Do I have a hole? Do I have a jump? Do I have anything? Nope. This is continuous. Again, the biggest thing that you're going to have to be real careful of is when it comes to the jump discontinuity, because sometimes people will mistake an infinite or a hole with another point below that as a jump. But remember, specifically when it comes to jump, I always like to refer to it as a break more than a jump. All right? So that's all I have for you. Finish your homework. Unit 8 homework. That'll be turned in tomorrow before you take your test. And then also work on your review. I will post the answers. Our answers should be posted with this video. So as always, come in for questions before your test. Hope all goes well, and good luck. See you soon.